Okay, you are given an array of integer stones, where stone's I is the weight of the ith stone. We are playing a game with the stones. On each turn, we choose the heaviest two stones and smash them together. Suppose the heaviest two stones have weights x and y, with x is less than or equal to y, right? The result of this smash is if x is equal to y, both stones are destroyed. If x is not equal to y, the stone of weight x is destroyed. The stone of weight y has the new weight y minus x. At the end of this game, there's at most one stone left. So at the very end of the game, they want us to return, if there's no stones left, return 0. If there's one stone left, right, return the weight of it, right? Those are the only two cases that we should have at the very end, right? So basically, while there are two stones to smash, they want us to just keep smashing them until there's either no stones left at all or one stone, right? So you can kind of imagine a couple examples in your head and see how they're, if we continue, if we have a set of stones and then we smash two together, and the result of smashing two stones together, the outcome is either no stones or one less stone, you're going to end up with eventually 0 stones or only 1 stone. Okay. However you do it. But, just kind of thinking about this problem, and let me just like restate it again, because the problem statement is like all over the place, but basically we're going to pick the 2 biggest stones, right? On each turn of the game, we're going to pick the 2 biggest stones, and then we're going to smash them together. What that means is if they're equal, like the stones are really just integers. If those integers are equal, okay, then we won't do anything, like as in we will just remove them from the stones and then that's it, right? On the other hand, if the smaller stone is, if one of the stones is smaller, then we actually put a new stone. We, instead of taking both of those away, we'll take them away, but we'll put one back, which has the weight of the difference between the top 2 stones, right? So, right. So the bigger stone minus the smaller stone, that is the weight of the new stone, which we'll put back in to the game, right? If you think about this problem a little bit, like we're going to have to be finding the maximum value of a group of values that isn't sorted, right? We're going to have to keep finding the max value, right? So that's really hard. The time complexity of that is just going to explode. It's going to be bad, right? So if we have to keep sorting, luckily there is a data structure which guarantees us that we always get constant time access to the biggest element among a list of values. So it's like, so that's a heap or a priority queue. A max heap is where you always have constant time access to the biggest value. Min heap is just the opposite, constant time access to the smallest value. Obviously for this, we want to be able to get the biggest stones. So we're going to use a max heap, and let me just show how this works for one example. And let's do 274,181. So let's do the same, example that they have there, just for a sanity test on our algorithm. So we're going to have a max heap. That's the input array. The first thing we're going to do, there's one drawback, right, to always having the constant time access to the biggest element. Anytime we want to insert an element into our heap or remove an element from the heap, that's going to be a logarithmic operation. So it's worse than constant, but it's not as bad as linear. It's still pretty fast, but just need to call that out for the time complexity, right? So we're going to first just add all of these elements from our array to our heap. So we'll have the 2, the 7, right? We're going to have constant access to that 7 now because it's the biggest element. So that was a logarithmic operation. That was a logarithmic operation. It's logarithmic with respect to the size of heap, right? So 7 goes in there, the 4, 7's still the biggest, put the 1, put the 8. Okay, 8, we got a new winner on the biggest element, right? So now we have constant access to the 8, and then put the 1 in. Okay, so we're going to basically loop while we have at least 2 elements, right? So while our max heap, the size of it is greater than or equal to 2, we want to try smashing stones, right? Because once we have 1 stone, there will only be, there's no stone to smash it with, right? So like we'll get some null pointer thing or whatever. We need to have 2 stones to get from our heap, right? So that's going to be the conditions for our loop. We're going to pop the top 2 stones, which will be like a constant time thing. So So y from the problem statement was the bigger stone. So at first here, we'll just say we'll go through the whole algorithm. So this will be like the first iteration of our loop. Y will be 8, and then we have to get the next element, right? So we'll pop that one. 7 is the next biggest. Pop that one, right? That was also constant. So x is going to be equal to 7. So these are our two biggest stones. They're not the same, right? So we're going to have a new stone to add back to our heap, which is bigger stone minus smaller stone, right? So y minus x, that's going to be 1. So we're just going to add a 1 back, right? New constant time access, biggest element is going to be this 4, right? Okay, so that was one iteration of that was like one turn of the game. Okay, so now we're going to get the next two elements. So y equals 4, x is going to be equal to 2. Okay, and then so yeah, so we don't need these anymore. And then we're going to have to add a new stone back, which is 2, right? Just the difference here. Okay, and then let's move on. So we have a 2 and a 1. We're going to have to add a 1 back. Okay, and then one of those 2 goes away, one of those 1s goes away, right? So now we have 3 1s. Okay, so let's play the game again. So we get the biggest 2 stones. These are the same, so they're both just going to go away, right? When they're equal, we don't have to add any stone back. Okay, so now we only have 1 stone left. We can't iterate again. So at the very end of this, we would just return a 1, right? It's 0 if there's no stones in the heap. If there's 1 stone left, just the weight of that stone. And just to double check that's correct, right, the output is 1, and there's one more. Or let's see, wrong example. Output is 1, right? So it's 1 on both examples, but right. So that checks out for the first example, just for a spot check there. For the time complexity, we're going to have big O of n times log n time. Because we have to look at every element in the array at least once. And then just for the first portion of the algorithm where we're putting every element from the array into our heap, right? It's obviously going to be n log n. Every insertion's log n. We have to look at every element in an array of size n as well, right? And then even after that, when we loop until our heap is completely empty, right? That one is going to be also linear, right? Also linear, right? In the worst case with respect to the time. So we're going to go with n log n here. And not linear, because even inside of that while loop, we have pop operation. So it's n log n. So it's like 2 n log n, right? But just with big O notation, it's going to simplify to n log n. So n log n time complexity, and then the space complexity is just big O of n, right? Because the heap scales linearly with the number of elements that are in it, and there can be as many as n elements, where n is the number of elements in the input array. So yeah, let's code this. So our heap in C++ is going to be a priority queue, and it's going to be of integers, and under the hood, we can just have that be implemented as a vector of integers. We'll call this max heap. We need to loop through our stones, right? So for stone in stones, we're just doing const reference to not make a copy and not accidentally modify the input array. So we need to say max heap dot push stone, just to put that into our heap. And then we're going to loop while max heap dot size, we said we need that to be at least 2. So while it's greater than or equal to 2, we're going to get the top 2 stones. So the biggest stone will be y. So we'll say int y is going to be equal to max heap dot top, right? We can get it in constant time. Then we can pop. So max heap dot pop, because we need to get the second biggest stone as well. And we're done with these stones in the heap at this point, right? By the time we've smashed them, right? So we're going to get that. We're going to pop it as well. So that's the second biggest one. And then we just need to check, right? We don't have to do anything if they're equal. On the other hand, if x is less than y, right? That's the only other possibility at this point. right? Because of how a heap works. So if x is less than y, then we can just say max heap dot push back. We can push back, or not push back, but it's just max heap dot push, and then the weight of the new stone, right, is the bigger one minus the smallest one, right? And then at the very end of this, we can just use a ternary, right, to see if the max heap still has elements. So if max heap, if the max heap is empty, then we want to just return 0, right? There's no weight because there's no stones in the max heap, right? But otherwise, if there is still one stone in there, which is the only other possibility, we'll just say max heap dot top. Okay, so that's pretty much it for this problem. So hopefully that helps, and I'll see you guys in the next piece.